So see here, the potential of a single electrode cannot be determined. For suppose if you are taking a single electrode and you try to measure the electrode potential of that particular thing. For suppose we know there is a cathode and anode. Okay. And we know there is a reactions will happen at the cathode and anode. So some oxidation reaction will happen, some reduction reaction will happen. So that will produce certain potential. Yes or no?
Yes, sir.
We also saw oxidative potential, reduction potential. So if you just only want to measure for one electrode, it is not possible. So remember, it is very fundamentally impossible to measure absolute potential of a single electrode. Okay, in isolation. That means when you want to just measure a single electrode potential, it is not possible. Understood this?
Yes, sir.
Yes,
Why
sir.
it is not why it is not possible? Okay, the reason is in order to measure the electrode potential, it requires a complete circuit. Okay, and a point of reference. So if you don't have a point of reference, if you don't have a complete circuit, then it's not possible. If you see at particular electrode, only half reaction is happening. Yes or no? We say that half cell reaction. So remember this. So impossible to measure absolute potential of single electrode when it is present alone. Okay, single electrode in isolation. The reason being requires complete circuit and point of reference. Okay, so remember, while single electrode potential cannot be determined directly, but you can measure it by seeing the difference between two electrodes. Okay, so remember, if it is single, you cannot measure, but you can measure when you have taken a reference. Okay, when you have taken another electrode which is acting like a reference. You understood this point? What is meaning of taking a reference?
Could I repeat, sir?
Do one thing. Okay, tell me this. If you want to measure a high altitude, how do you take the reference? How do you measure an altitude? For suppose you are at a particular height. Let's say you went to Nandi Hills and you say, I'm at this particular height. How do you measure?
So from sea level.
Yeah, from sea level, right? So here, what is this sea level? That's a reference point. So taking this as a reference, now I am measuring the altitude. You understood this?
Yes, sir.
Okay, the same way here, it requires complete circuit. That's one thing. Okay, and another thing is point of reference. So here also, in order to measure what is the potential of that particular electrode, you need to take some reference. That reference acts like a zero thing, 0 point. From this 0 point, whatever the potential difference is there, you will be measuring. It could be the positive or it could be negative. We'll see what is the positive and what is negative. Is this clear?
Yes, sir.
Yes, sir.
Any doubts?
No, sir. No, sir.
Okay, so just remember, single electrode potential can't be determined directly, but potential difference between two electrodes can be measured with high accuracy. Okay, by taking I'll be writing here. Just remember. By taking the reference electrode. So is this clear?
Yes, sir.
So see here, the potential of a single electrode cannot be determined. However, the potential difference between two electrodes can be measured accurately. The potential of an electrode is calculated using a reference electrode. So these 3 points clear, right? So now see here. So what is saying here? An electrode is chosen as a reference with respect to which all other electrodes are valued. Standard hydrogen electrode is considered as the standard reference electrode. It is electrode potential which is arbitrarily assumed to be 0 volt. You understood? So what we are doing here, we are taking a reference electrode. Okay. So remember, we are taking a reference electrode. So what is this reference electrode? If you take a electrode potential system, okay, so one will be a electrode. Let's say we don't know what is this electrode. Okay, so this is an unknown electrode, and we are taking a reference electrode here. Okay, this reference electrode I always know. Okay, there is a standard things you will be maintaining for this. I'll tell you what are those. Okay, but this one I don't know. So let's take how we calculated like the height of the any altitude where you are taking from the sea level as the 0. From that you calculated the height. The same way here the reference electrode will be taken as the 0, and from that you will be calculating this electrode. Either it could be the positive height or it could be the negative height. The same way here it could be the positive potential or it could be the negative potential. But here the reference electrode will always be 0. So remember this. The SHE will be 0, and from that if you move the right it will be positive. If you move the left it will be negative. Understood? I'll tell you what are these positive and what are these negative potentials comes. Is this clear?
Yes, sir.
Yes, sir.
Okay, so just remember this will work similarly like you are measuring altitude relative to the sea level. The same way here also you are measuring a particular electrode potential by taking the reference electrode as a 0. Here the reference electrode is nothing but SHE, standard hydrogen electrode. Okay, so remember this reference electrode, it is nothing but SHE, she, where we call it as the standard hydrogen electrode, which is the primary reference. Okay, with this you will be measuring any electrode. Okay, whatever the electrode is given, whatever the chemical reaction happened at this electrode, but this will be taken as a 0. Here this is always you will be taking the hydrogen, because hydrogen will be 0. I'll be showing those. But the other one will be unknown. We need to measure that unknown by using this. Clear? So this is also called as the universal standard reference electrode. So remember this. So this is also called as universal standard reference electrode. Okay, so using this standard reference electrode against all the other electrodes, you will be measuring the potential. Okay, and remember this is exactly the 0 volts. This is exactly the 0 volt. By using this, you will be measuring all the potentials of the other electrodes. Okay, so other electrode potential can be measured. Clear? Why do we use this standardization? I'll tell you what are those standardizations. I'll show you. But why do we use this standardization? Okay, one thing, it will provide a consistent basis for comparing different electrodes. For suppose if you are not maintaining the standard things, and if you have taken arbitrarily the values, the temperature, the molarity of the chemical solution, then these values can be changed. This will not be standard. Yes or no? If you are changing the height of the sea level, at one point you are taking this as a sea level, at some point you will be taking this as a sea level. If you are changing this, can you be given the accurate height of the particular altitude?
No, sir.
No. The same way here, we will be taking a standard things. I'll tell you what are those standard things. What is the temperature should be maintained? What is the molarity should be maintained? All those. Okay, so remember it will be helpful for consistent basis for comparing different electrodes. Okay, and it will be helpful for creating the electrochemical series. I'll tell you what are those electrochemical series. Okay, and it will enable to calculate the cell potential accurately. Okay, in an electrochemical cell. You understood this? What is the use for making this hydrogen electrode as a standardization?
Yes,
Sir.
Okay. So now see here, electrode potential of SHE at
Yes, sir.
anode at cathode. Okay. Standard hydrogen at anode at cathode. So let's see. So first of all, this is the half cell reaction. Can you tell this is the hydrogen? Yes or no? That means I'm taking my SHE, the standard electrode. Either I'll take at the anode, either I will take at the cathode. If I take at the anode, what will happen? Which reaction will happen at anode? Come on, guys. Which reaction will happen at anode? If I take the hydrogen at anode, which reaction will happen at anode? Sharon, you tell me.
Oxidation.
Huh?
Oxidation.
Okay, Sharon says oxidation. What about you, Shrikar?
Yes, sir. Correct. For anode.
Banu? What is the
Sir,
reaction will
anode.
happen at cathode?
So it was reduction, sir.
I told you in the last class, CR. That means at cathode, reduction will happen. AO. At anode, oxidation will happen. Yes or no? So if I take the hydrogen, the SHE at anode, what happened? It will result in oxidation reaction. If I take the hydrogen at cathode, it will result in reduction reaction. For suppose you see here, what is this reaction? Can someone say? What is this reaction?
Oxidation.
Banu, is it oxidation?
So,
Yarashikar is oxidation. Huh?
no, sir, it's reduction.
Reduction.
Yeah, it is a reduction reaction, right? So what about this?
So it is oxidation, sir.
Yeah, this is a oxidation.
Sir,
Perfect.
this is
Super,
reduction,
super,
sir.
super,
Sir, this is addition of electrons and there's losing of electrons.
super. Banu, Shikar, super. Banu, how many times should I say? After the reaction, if the electrons are released, what we call that as? Oxidation. It is donating the electrons. The product is formed, that product is also formed with the electrons. See, this is the A. This A, it is turned into B by releasing the electrons. So it donated the electrons. So what do we call this as? Oxidation. This is a oxidation. For suppose you have a B, this B, it is taking the electrons and it is forming the A. You are giving the electrons before the reaction itself, so that it is reduced and it will form A. So what do we call? This is a reduction. Yara Shekhar, huh?
Yes,
Banu,
sir.
what happened?
Sir, I said oxidation.
తర్వాత రిడక్షన్ అన్నావు కదా.
Sir, you are like
కన్ఫ్యూజ్ చేస్తా. అవునరా, నేను కన్ఫ్యూజ్ చేస్తా. నీకు తెలీదా? నీ పేరు శ్రీకర్ కాదు. అవునా, నీ పేరు శ్రీకర్ కాదంటే అగ్రీ చేసేస్తారా? కన్ఫ్యూజ్ అవుతావా? Come on, guys, don't confuse. Just think before you answer. So see, the reaction has happened and liberated the electrons. So it is oxidized. Oxidized means what? Release of electrons. Remember, oxidation means release of electrons. Understood? So what's happening here? The oxidation of hydrogen gas has happened and it is releasing the electrons there. Okay, and it formed the hydrogen ion. So tell me, where does this reaction will happen, Banu? Where does this reaction is happening? Where does this half cell reaction is happening?
So anode, sir.
Yeah. So this is the half cell reaction at anode. So just remember, guys, the half cell reaction at anode where oxidation of hydrogen gas to hydrogen ions and release of electrons. I'm just writing it so that you will not confuse again. Okay, so remember, this is the electrode potential at anode. Okay, so if you see here, this is H2, it is giving rise to 2H plus 2E minus. So oxidation potential is equals to E H2 by H plus. I told you how to write this one. Okay, and this same oxidation potential, but we are doing at what condition? At a standard condition. So under standard conditions, under standard state, the same reaction, it will be written like SOP, that is standard oxidation potential, is equals to E naught H2 by H plus. So remember, E naught will be referring for the standard potential, for the standard state. Clear? Any doubts?
No, sir.
No, sir.
No, sir.
Sharon, what about you?
Understood.
ఏం శరణ్ మాట్లాడట్లేదు?
No, sir. Bluetooth disconnect అయ్యింది.
సరే. So remember, SOP means standard oxidation potential, and it will be denoted by E naught H2 by H. Okay, so remember, if it is normal oxidation potential, you will be giving this way. But if it's the reduction standard state, you will be giving this way. Okay, so what is this standard state? Okay, so what are the conditions needed to maintain this standard state? One is 1 atmospheric pressure. So 1 atmospheric pressure, 1 molar concentration, and temperature 298 degrees, 298 Kelvin temperature. So in terms of degrees, how much it will be? 298 will be? Tell me, 298 Kelvin in terms of Celsius, how much? Sometimes they can give you at Celsius also. At that time, you should know in terms of Celsius as well. Come on, guys, 298 Kelvin into Celsius. How much? You might have studied in class 11th how to convert the Kelvin into the Celsius. What is the 0 degree Celsius for in terms of Kelvin? Come on, guys, what is the melting point in terms of Kelvin? Have you ever heard the word number 273.15?
Yes, sir.
So
Yes,
273, how much if I add, that will come into 298? $25. Yes or no? 273, if I add 20, it will be 293. If I add 5, it will be 298. So we know that 273.15 Kelvins, it's nothing but 0 degrees Celsius. And if you add 25 units, this is a 25 degrees Celsius. Remember, okay? So just minus 298 minus 273. It will be giving in terms of Celsius. Come on, guys, this is a very basic thing. You should not forget it. So this will be 25 degrees Celsius. Understood? Is this clear?
Yes. Yes, sir.
So why do we are calculating the electrode potential? Tell me. I already told you before. What is the use of this electrode potential?
Yes, sir. Yes,
So
sir.
it will be giving the direction of the electron flow. So you can get the direction of the charge flow. You will be getting, if you know what is the E naught value, you can also tell the Gibbs energy, or you can also tell whether the reaction is spontaneous or not. Yes or no?
Yes, sir.
When does the reaction will be spontaneous? If E naught will be positive or negative? So you guys didn't study anything.
Negative, sir.
Super. Gibbs energy negative unte, when Gibbs energy is negative, the reaction will be spontaneous. When the Gibbs energy is positive, the reaction is non-spontaneous.
Yes, sir.
If you take E naught value should be positive for the spontaneous reaction should happen. The electrode potential should be positive, not the negative. Don't confuse between the Gibbs energy and the electrode potential. And it also tells us what will be the strength of reducing agent. Please watch the previous class or study the PPTs. Okay, so in this case, hydrogen is itself the reducing agent. Clear?
Yes, sir.
So this is what the electrode potential will determine. So we need to find out that electrode potential. So just understand that I'm repeating again. So electrode potential, it can be calculated at anode or cathode. Okay, that means the standard. Okay, hydrogen, the standard hydrogen. Okay, so remember, if it is at anode or if it is at cathode, if it is at anode, the oxidation reaction will happen. If it is at cathode, the reduction potential, so the reduction will happen. Okay, so at anode, you will be calculating standard oxidation potential, that's a SOP. At the reduction, you will be calculating it as the standard reduction potential. Remember this. So why we are saying it as a standard? Because we will be maintaining the standard conditions like 1 atmospheric pressure, 1 molar concentration, 25 degrees Celsius or 298 Kelvin temperature. Okay, this will be acting like a reference point. The SOP will act like a reference, or the SRP will act like a reference. From that, you will be calculating the unknown potential of the any electrode. Clear? So you can see here, this is the reduction potential. Okay, so for normal reduction potential, we will be giving it as EH plus by S2, but under standard state, we will be giving it like standard reduction potential. It will be equal to E naught H plus by S2. Clear?
Yes, sir.
Sir.
Chapande sir. Any doubts on error, Shikhar?
No, sir.
Okay, so this is also, here also you will be maintaining the standard state, like 1 molar concentration of the aqueous species. You will be taking 1 atmospheric pressure gases. Temperature will be 25 degrees Celsius or 298 Kelvin. Okay, and this is called as the standard reduction potential. Okay, so what's happening here? The hydrogen ions were reducing to hydrogen gas. Okay, so hydrogen ions reducing to hydrogen gas. So this we call it as the reduction. And this reduction will happen at cathode. Clear? By seeing the reaction itself, you should be able to tell whether it's happening at anode or cathode. Okay, if it is reducing, we call it as it is happening at cathode. If it is oxidizing, we will say it's happening at anode. Remember CR class representative or the cathode reduction. Okay, so reference potential, electrode potential of SHE is taken to be 0 at all temperatures. Okay, so remember, it should be always the 0. So standard oxidation potential, it will be equal to standard reduction potential. That will be equals to 0 volts. Clear? Here, always the standard oxidation potential will be with opposite sign to the standard reduction potential. Notice that thing. Any doubts?
No, sir.
No, sir. No, sir.
Okay. So next one, to calculate the standard potential of any other electrode, it is coupled with SHE. Okay, see here, we are not saying SOP or SRP. It could happen at anode or it could be happen at cathode. If SHE is happening at anode, we will be calling it as SOP or SRP. Banu, you say? If SHE is happening at anode, we'll be calling it as SOP or SRP.
So, you don't know, sir.
Banu, just think. I told the SHE, that is nothing but the standard hydrogen electrode. Okay, this
Yeah.
standard hydrogen electrode, if it is happening at anode, what do we call? Anode. Anode, what is the reaction is happening at anode?
So it is oxidation, sir.
Then we will call it as SOP or SRP.
The SOP, sir.
Yeah. Okay. So remember, guys. So it could be SOP or SRP. SOP if it is happening at anode, SRP if it is happening at cathode. Just notice this. And what is this SHE? Standard hydrogen electrode. Remember this. Standard hydrogen electrode. Okay. So what we are doing the electrode coupling. Remember this. We are doing electrode coupling. What is this electrode coupling? See, this will be the first step. Okay. So what we are doing, we are coupling the electrode of our interest with the standard hydrogen electrode. First, suppose let me say this way. I have a different electrode potentials. Like I have a different electrodes. Let's say the electrode A, B, C, D, E. These are the 5 electrodes I have. I want to find out what is the value of this A. Okay. What is the value of this A? What is the electrode potential of this A? What is the electrode potential of B? What is this electrode potential of C? What is the electrode potential of D? What is the electrode potential of E? These are all unknown unknown electrodes. I need to find out what are their potentials. How do? I will take this A together with SHE and I will find out what is A. I will take B with SHE and I will find out what is the potential of B. The same thing, I will take CDE and I'll together with SHE and I'll find out individually the CDE. It's like, for suppose you are having different hills like Nandi Hills, Tirumala Hills, and you are having some Aruku Hills, okay, Ooty Hills. So these are all different altitudes, but I want to find out individually what are their heights. So I'll be taking the sea level height and I'll be measuring what is the altitude of this, what is the altitude of this, what is the altitude of this, what is the altitude of this. The same way I'll be finding out A, B, C, D, E by taking in couple with SHE. So here this one and this one. This will be taking like SHE, this will be A, this will be B together with SHE, C together with SHE, D together with SHE. So these two are couples, these two are couples, these two are couples, these two are couples. You understood? What is meaning of coupled with SHE?
Yes, sir.
Any doubts?
Yes, sir. No, sir.
So remember, this SHE will be acting like the universal reference point. Okay, so with this universal reference point, I will be able to find out any electrode potential. Remember this. So SHE, universal reference point. Okay, so with that universal reference point, I will be able to find out electrode potential of any electrode of our interest. Okay, electrode of interest or find electrode potential of any unknown electrode. Clear? Its potential is measured, which gives the value of standard electrode potential of that electrode. Okay, so what we are doing when we are taking an electrode and you coupled with SHE, the potential difference between the two electrodes, one electrode is the unknown electrode, the other electrode is SHE. So between these two, whatever the potential difference is there, okay, so this potential will tell us the potential difference. Okay, it will help us to find out. We'll be solving certain sums. You will be understanding how we'll measure. You understood? So how does this potential is measured? We'll be taking the unknown electrode. It could be A, B, or C. It could, or you can say the electrode of our interest, and we'll be taking the other electrode, which is the SHE. Okay, the universal electrode. So we will be finding out what is the electrode potential difference between these two. So this will be always 0. For suppose this is 2.78, then I'll be getting that potential difference as 2.78 volt. And this is the electrode potential of A. Or if I'm getting minus 2.5, then I can say minus 2.5 volt is the potential of the A. You understood? So it will be directly representing the standard electrode potential that has to be tested and with the unknown. Clear?
Yes.
Yes.
You understand the point? Its potential is measured, which gives the value of standard electrode potential of that electrode. You understood that?
Yes, sir.
That means we are taking this standard, okay, hydrogen electrode. So this standard hydrogen electrode, it could be SOP or it could be SRP. Yes or no? Standard oxidation potential or standard reduction potential. If it is SOP, then my unknown potential will be SRP. If it is SRP, my unknown potential will be SOP. So that's what he says. So we will not just simply get the oxidation potential because we are doing this entire reaction at standard condition. So whatever the unknown also, it will also come as like SOP or SRP. So that's what its potential is measured, which gives the value of standard electrode potential. It could be standard oxidation potential or it could be standard reduction potential of that electrode. Clear?
Sir.
Yes, sir.
Any doubts, Banu, Sharon,
No, sir.
others?
No, sir.
Sir.
So this is all what we understood so far. We calculated the E cell, we saw the properties of electrode potential, we determined the electrode potential, we also calculate the standard electrode potential. And still, what we will be continue to learn is calculation of standard electrode potential. That means we just saw, okay, the formulas, but we'll be measuring, we'll be doing a problem, we'll be seeing the half cell potential, we'll be seeing the standard electrode potential, electrochemical series, galvanic cell, Daniel cell. Electrochemical cell, sorry, galvanic cells and Daniel cells will do tomorrow, but we'll stop here. Electrochemical series for today's class. Okay.
Yes, sir.
So are we good to go or anyone feeling sleepy?
So they can go ahead.
Okay. Okay, fine. Okay, so we understood, right? What is meaning of standard electrode potential? To calculate the standard potential of any other electrode, we are coupling with SHE. Yes or no? So its potential is measured, which gives the value of standard electrode potential of that electrode. First, suppose let's see. Okay, here is the cell is given. Okay, let's construct a cell where at anode the zinc electrode is present, and now our standard potential, the SHE is present at the cathode. So from this, can I tell this SHE is the standard reduction potential? Yes or no? Because it's happening at cathode. Cathode, we know the reduction reaction will happen. So at cathode, the She is called as SRP. If it is happening at anode, the She is called as SOP. Yes or no?
Yes, sir.
So,
Yes, sir.
okay, just remember it is the SHE at cathode. And E naught cell is given as 0.76 V. Okay, and the reaction is happening at 298 Kelvin experimentally. So it's happening at the standard condition only. So what is given? Just understand. At anode, the zinc electrode is present. In cathode, we are taking the SHE. This will be acting like my reference. So this is a universal reference. Okay, and we know what is the E naught value of this cell potential. It's a 0.76 V. So we know the formula. E naught cell is equals to E naught cathode minus E naught anode. Remember this formula. Order also. It's a cathode minus anode, not anode minus cathode. Okay, just know this. So now write down the form. So E naught cell is equals to E naught cathode. How does the reaction will happen? SHE. SHE, that too it is a SHE, that too it is reducing. Okay. So reducing means we can give it like H plus ions. Ions are reduced to hydrogen gas. Yes or no? You understood why I'm writing it like H plus by H2? You should know sometimes the question will simply ask what is this? That's it. He will give you H plus by H2. He will be giving in the other option H2 by H plus. You should be able to understand this. Is this clear? Why I'm writing H plus by H2?
Yes.
Yes, sir.
Because
Yes,
at
sir.
reduction, we know H plus certain electrons, it will convert into the hydrogen. Yes or no? So 2H plus 2E minus, it will be converted into H2 gas. So that's a reduction is happening. So that's the reason we will be writing H plus by H2 minus anode. Anode, the what is happening here? Oxidation is happening. So Zn plus 2 by Zn. Okay. So see here. One second, guys. Okay. So we know that E naught cell is given like 0.76, and we know this is the standard potential. Yes or no? This is a reference point. So I can take SHE as this is the SHE. So I'll be putting in the bracket, this is the SHE. So this will be 0 because hydrogen. So that's SHE minus E naught Zn plus 2 by Zn. So this will be E naught Zn plus 2 by Zn is equals to minus 0.76 V. Clear? Understood this?
Yes, sir.
Yes, sir.
Yes, sir.
So the value will be minus 0.76 V. Okay. So remember E naught minus 0.676 V. Okay.
So go to the previous slide 1 second.
1 second. 1 second. One second. Just give me 1 minute.
Once.
Here I wrote something wrong. Have you noticed?
So it's Zn and Zn2 plus.
Yeah. Yeah.
So in oxidation, it's Zn slash Zn2 plus, right?
Yes.
Zn.
Yes. 1 second. Okay, actually, there's a thing. I'll tell you why. I'll tell you this later. But just remember, whenever, even if we calculate E naught at anode, they, I don't know why, but the material has taken like this only. Okay, so E naught is equal to Zn plus 2 by Zn. That means they are taking it like a reductional potential only. Okay, even though it's happening at anode, but they are showing this as a reduction potential. And whatever the value you are getting, this is the E naught Zn by Z2, which is a reduction potential. Okay, see, it's happening at anode, but still they considered the reduction potential here. They didn't consider the oxidation. So they are considering it as a reduction potential, and you will be getting minus 0.76, which is a reduction potential of that at anode. But we need to find out the oxidation tendency. Okay, in order to find out this oxidation potential tendency, what they are doing now, they are inverting it. So Zn by Zn plus 2, they are taking it like 0.76 V. So during the calculation, they are taking it like reduction potential. Understood? So this is how the thing is like. So Zn is giving like Zn plus 2 plus 2E minus. This is actually the oxidation reaction. But they are calculating the standard electrode potential of the off reaction. They are getting minus 0.76 V. Okay, but still, this is a reduction potential. This is not the oxidation potential. Okay, note this thing. So as it is a reduction potential, now they are converting into the oxidation. So for that oxidation, now minus 0.76, it was turning into 0.76. Clear? They are taking like minus of minus 0.76. So they are taking it like positive 0.76. Is this clear?
Yes, sir.
Yes, sir.
Nitya, what
Yes,
about you?
sir.
Understood this,
Yes.
right? So just for now, you keep it like that. Whenever they are calculating like a reduction potential only. Okay, even though it's an anode, but they are not taking it like a oxidation. Maybe anode cell, they are taking it like, once just go back the formula. So this is, we considered. Okay, so SOP plus SRP, it should be 0. So in that case, we got this. Okay. So we are taking it like the entire cell, no? So it's a E naught cell. That's given like 0.76 volt. Okay. So this E naught cell is together of SOP plus SRP. So SOP plus SRP, it is giving like 0.76. But we know the standard zinc we took. Okay, we took it as cathode, so it will be 0. SOP is equal to 0.76. You understood this? So SOP is equal to 0.76. Clear? Is this clear or any doubts are there? Let me know.
Yes, sir.
So
Yes.
see here, I mean that formula, if we do that way, we are taking it like negative. But if you are taking E naught cell is nothing but SOP plus SRP, that's equals to 0.76. SOP, we know standard oxidation potential plus 0 is equals to 0.76. If you directly calculate. But what they did, instead of taking SOP, is taking like minus of SRP. You understood? Now why the formula here, it got the minus value. You can take it like E naught plus this one. You can take plus, but he is taking like minus of minus SRP. That's how he is taken. Okay, minus of SRP. He has taken reduction potential instead of taking oxidation potential. Is that clear?
Yes, sir.
So just notice that thing as well. Okay. Any doubts here? Or everything is clear?
Clear, sir.
Yes, sir.
Yes, sir.
Okay. So remember, so here this is 0.76 and hydrogen, we know it is 0. Okay. That means with respect to hydrogen, zinc has the more tendency to get oxidized. So whenever it's positive, it's oxidized. Whenever it's negative, it will be reduction. Okay. The negative reduction potential will be minus 0.76. The oxidative, this, let me write here. This will be reduction potential. So reduction potential. This will be oxidation potential. So if you are taking the oxidation potential, it is positive. If you are taking the reduction potential, it's negative. So from this, I can say with respect to hydrogen, zinc has greater tendency to get oxidized. Understood? So you can see here the value. If you see, measure that by using this, you will be get voltmeter, you will be getting 0.76V. So similarly, standard reduction potential at 298 Kelvin for many other electrodes are calculated. They are arranged in a series. Their descending order of electrode potential is known as electrochemical cell. Okay. So remember, if you want to calculate the standard reduction potential, that's also maintained at the standard conditions like 298 Kelvins and 25 degrees Celsius or 25 degrees Celsius. Okay. So that it will be giving the standard, okay, condition, so that you can take it like a universal condition and you can refer and you can measure any other electrode potential. Okay. Any other electrochemical off reactions. Okay. And if you keep all these electrode potentials, so all these electrode potential in an order systematically. Okay. So systematically, if you organize them, okay, they will be forming the electrochemical series. So they will form the electrochemical series. Like if you remember, you are putting all the bulbs or circuits and you are putting the resistance in a series, like in a particular order. So how it is influencing the same way, if you put all the cells in a series, then it's a electrochemical series. Okay. And these series arrange the electrodes in descending order or ascending order. Okay. Based on their potentials. You can take the oxidation potential or you can take the reduction potential. So remember, SRP, that's a standard reduction potential for various off cells are measured at same 25 degrees Celsius or 293 Kelvin. Okay. And if you put them in the order in decreasing order, then we call it as the electrochemical series. So this means you are taking the She as a 0 volt. Okay. And you put them in the descending order. Okay. And put in descending order. So that's nothing but the electrochemical series. I'll show you examples. But have you understood this statement? Any doubts in this?
No, sir.
Okay. Now you see here. For suppose, let me take, these are all oxidation things. Okay. So remember, these are all oxidation things. First, before, let me tell you one thing. Notice these points. Okay. So notice this one thing we need to organize. Okay. Arrangement pattern. So we are organizing them based on elements are ordered. How we are ordering? Ascending order or descending order? Come on, guys, tell me how we are organizing, ascending order or descending order? Just now I told descending order. Okay, descending order means what? From a bigger value to lower value. Yes or no? Am I audible?
Sir, can you repeat, sir?
See what I told. We are taking the she as a 0 volt. Okay. So you are considering it as a 0 volt. From that, you are arranging the reduction potentials in descending order. Descending order means what? Big value to small value.
Yes, sir.
Okay. So that means elements are ordered by decreasing standard reduction potential. Or you can take it like SRP, decreasing standard reduction potential. That means the species above hydrogen. So we know hydrogen is a 0 point. Okay, the species above hydrogen, they have a negative reduction potential. And if you take the species below hydrogen, they will be having positive reduction potential. So what does that mean? So if it is a more negative potential, if it is the negative value, if you increase more, that means it acts like a strong reducing point. Understand this. Okay. So remember, if the negative value before the reduction potential increases, okay, that means if you take -5, -4, -3, here -5 is greater. So this will be strong reducing agent. So strong reducing agent. And this will be strong oxidizing agent. Or you can take it like the highest number will be oxidizing agent, the least number will be reducing agent. Is that clear?
Yes,
Yes, sir.
Okay,
Yes, sir.
Sridhar, Mandara, Banu, only three
Yes.
understood.
I
Nitya, are you
understood,
there?
sir.
What about you,
Yes,
Sharon?
sir.
Sir, I said yes.
Okay. So see here, this is the, tell me now, is this a strong reducing agent or strong oxidizing agent? Nitya, what do you say? The first one is strong oxidizing agent or strong reducing agent?
So strong oxidizing agent.
What about you, Shrikar?
Yes, sir. Same.
Banu, Mandara, Sharon?
Reducing.
ఏంటి Sharon? Strong reducing agent, strong oxidizing agent?
Strong reducing.
Oxidation.
Sharon, ఒకసారి ఇక్కడ నేను ఏం చెప్పాను? The negative value of the reduction potential, if it is greater, that means if you take -5, -4, -3, this is the greater value, then what it will be? Strong reducing agent. But if you are increasing the positive value, +5, +4, +3, then this will be the strong oxidizing agent. So what is here? Plus 2.87. So this will be strong oxidizing agent. Understood?
Yes.
So for suppose if I write in the number line, if I write it like -4, -3, -2, -1, 0, +1, +2, +3, +4. So this will be strong reducing agent. This will be strong oxidizing agent. And whatever the 0 is there, this is nothing but SHE, standard hydrogen electrode potential. Is this clear for everyone?
Yes.
So all
Yes,
these will
sir.
come under oxidation. All these will come under reduction. So see here, if you just observe here, what's happening here? Oxidation is happening here. 2E is just joining with the iron. So 2F minus is formed. Sorry. This is a reduction. But yeah, this will be oxidizing agent. Okay, so here iron, for suppose just remember these are off reactions. So till they have a positive values, they will be acting like a strong oxidizing agent. I'll show you other examples as well. So see here, these are all positive. You don't need to remember, but at least know that which one will be acting like oxidizing agent and which one will act like a reducing agent. So just understand, you make out a list: iron, cobalt, H2O2, MnO4 minus. H2O2 is it oxalic acid, right? No, no, no. Oxalic acid is COH twice, I think.
The H2O2 is peroxide, right?
Yeah, peroxide, right? Yeah, yeah. Okay, guys, just okay. So remember, these are all off reactions which are oxidizing, acting like a strong oxidizing agents. And they're here. Okay, notice this thing. So this is our hydrogen which acts like a SHE. Okay, and then again you will be having all our negative values. Understood? See here, all the reactions we are taking only like reduction reactions. Okay, so if you see, all are just hydrogen electrons were added to the compound. So all these are reduction reactions. So when does the reaction will happen? Reduction reaction will happen when you have a strong oxidizing agent. Yes or no? Because this strong oxidizing agent, it will donate the electrons. It will be taking out the electrons. Yes or no? What is the strong oxidize? So what do we say when something is oxidizing agent? What do you say? Tell me. What is reducing agent and what is oxidizing agent?
So reducing agent it gets oxidized itself and reduces the other. An oxidizing agent gets reduced itself and oxidizes the other element.
Yes. Okay. So just understand that when do we say it's an oxidizing agent? Okay. So in the reduction reaction, okay, the one which has the ability to accept the electrons from the other substance, okay, and making them others to undergo oxidation, we call it a strong oxidizing agent. Yes or no? For suppose if you have A and B, if you say B is called the oxidizing agent, then what it will do? It will capture out all the electrons from the A. Okay, it will capture all the electrons from A and it will be taken up those electrons. Clear? For suppose if you have a reducing agent, what happens? For suppose the same thing, let's say C and D. Let's call the D is a reducing agent. What does it will do? Here it is capturing out all the electrons. Now here reducing agent, what it will do? It will donate the electrons. And it will make the other one to reduce. Okay, oxidizing agent, it's not oxidizing. It is taking out the electrons and it is undergoing reduction. Here, reducing agent means it is oxidizing and making the others to reduce. Understood? So in this case, this is reducing, this is oxidizing. In this case, this is reducing, this is oxidizing. Is this clear?
Yes.
Yes, sir.
Rikar, Sharan, understood or
Yes,
not?
sir.
Yes, understood, sir.
Okay, so just understand that which are all comes under oxidizing agent, which are all comes under reducing agent, you should notice it. Okay, so just make a small list, put all the AUC, LCR207, like the values above than the zero, and take out all the elements which are below the zero. Okay, you need to take out all these things and make a list. You should know that list. That's very, very important. You don't need to know the exact value, but just try to remember which one is a strong reducing agent, which one will be acting like a strong reducing oxidizing agent. Clear? Any doubts?
No, sir.
Sir.
Okay. So before I'll just I'll tell you few SRPs which are few applications of these SRPs which are very important. He will give you a list of elements, and he will ask you which one is a strong reducing agent, which one is a strong oxidizing agent, like that. Okay, we'll solve questions, you will understand at the time. So just understand that what is the use. So applications. We'll talk each of these applications in detail, but just now understand. First one, it will be helpful for predicting the oxidation and reduction behavior. So remember, first one is helpful for predicting oxidation, reduction behavior. For suppose, if it is higher SRP, higher standard reducing potential, so greater tendency to be reduced. If it is lower SRP, greater tendency to be oxidized. That's one thing. Second one, it will be helpful for determining the reduction feasibility. Okay, so determine reduction feasibility. We'll be seeing certain questions regarding this. That means whether the reaction will happen or not, it will tell by taking out certain chemical. So helps to predict whether the reaction takes place or not. Okay, that means spontaneous reaction happens or not. Helps predict spontaneous reaction, and also helps in calculating EMF. So calculate cell EMF value. I told you what is meaning of EMF. If you don't remember, just watch the previous one, electromotive force. Next one, it will also tell us the metal reactivity. So what does that mean? First, suppose metals in the higher series. So metals in higher series can displace metals in lower series. From their compound. It's like a displacement reaction. You know, right? For suppose if A and B is there, A will be replaced with a C or D. So based on which one is very good oxidizing or reducing agent. So I'll show you certain examples regarding this. So this is the one thing, metals higher in series can displace metals lower in series from their compound. Okay, so it will help us to find out the displacement reaction. So between metals and salts. For suppose in the salt you have a stronger metal. The stronger metal can replace this lower metal. Okay, so remember like that. So what are the factors will affect the standard reduction potential? So factors affecting SRP. So one is the atomic properties. The other one is environmental factors. So environmental factors, the other one is atomic properties. So what are these atomic properties? Let's say electronegativity of a particular element, ionization potential, atom size. These are not just know it, okay? And the other one is electronic configuration. Here, hydration effect on ions, temperature, concentration, pressure. We know, right? So I told you 1 atmospheric pressure, concentration, 1 molar temperature. 293. So all those things. So see here, just the same thing. So application of electrochemical series. So first one, species, particularly metals having highly negative SRP are powerful reducing agent like lithium, sodium, calcium. You can see those values here. Okay. So you can see those values and you can say why they are strong reducing agent. Next one. So species having highly positive SRP are powerful oxidizing agent. Okay, so based on negative value you are taking or positive value you are taking, so they will be acting like a reducing agent or oxidizing agent. You can take the Ft MnO4 minus. You can also check here. Okay, so F2 you can see here. This one 2.87V. That's the highest positive value. So that's why it will be acting like a strong oxidizing agent. Okay, so next one. So more active metals can displace less active metals. Okay, for suppose if I give you a reaction like this, so CuSO4 plus Zn, it says that Cu plus ZnSO4. I told you the displacement reaction. Yes or no? So here if I take a ZnCl, that's a zinc chloride. So this zinc, which is a displacing the copper. Why? In this reaction, the zinc metal is more active than the copper. I told you here the reason. Okay, so metal reactivity. Metal in higher series can displace metal lower series. Because of their higher activity, they can undergo displacement reaction. You understood this? So just understand that. So zinc displaces copper from sulfate from copper sulfate. The reason being zinc is more active than copper. Next one. So now tell me, if I write down the reaction like ZnSO4 plus copper, Sharon, tell me what will be the product? Sharon, are you there in the class?
Yes, sir.
Tell me what will be the product?
Zn plus S4Cl.
Okay, Shrikar, you tell me what is the product? Formed. For suppose if I react the copper sulfate with zinc, it formed the copper and ZnSO4. The same reverse reaction is happening. So what will be the product?
Zn plus CuSO4.
Zn plus CuSO4. Okay. Nitya, what is the product? The reverse reaction is only happening now. Nitya,
Sir, sir, but then copper cannot replace lead, sir.
yeah, this is what I told you here. Metal in higher series can displace the metals lower in series from their compounds. So displacement reaction will happen. But if you see here, the copper and zinc, here the zinc is more active than the copper. So it could able to displace the copper. But here the zinc is itself the more active. How can the copper will displace? So there will be no reaction in this case. Understood, Sharon, Shrikar,
Yes, sir.
and others?
Yes.
Banu?
Yes, sir.
So no reaction will not take place because here copper being a less active compared to the zinc, so it cannot displace the zinc. So no displacement reaction will happen. Here displacement reaction happens. So displacement will happen in this case. In this case, no displacement. So that's it. Any doubts?
No, sir.